Hello again. This is Math 2233 coming to you from the College Uta page. And this is the conclusion of the lecture entitled Implicit Differentiation, Gradients, and Directional Derivatives. As always, I remind you to be an active learner while you watch this video. When last we adjourned, I left you working on this problem where you had to use this contour plot of temperatures in Nevada, and you were to use this plot and the directional scale to estimate the value of the directional derivative of the temperature function at Reno in the southeasternly direction. So if you solve this, congratulations. If not, I will give you another opportunity to do this so you know what to do. Let's see how you did. Okay, the unit vector directed southeast is I minus j, and then this is divided by the square root of 2 to make it into a unit vector. But we're not really using a calculation here, we're just doing an estimate. So what we're doing is we're looking at Reno, and we see that nearby Reno, there was an area where the temperature was 50 degrees. Reno sits in an area where it is 60 degrees, and then we're going, in this southeast direction. So you can approximate the directional derivative, the derivative in the direction of u that we talked about going southeast of t by operating on t by the average rate of change of the temperature between the points. This line intersects these isothermals t equal 50 and t equals 60. And so what we do is we can say that the directional derivative in that u direction of t is approximately 60, which is the temperature in Reno, minus 50, the temperature in the point northwest of Reno, divided by the distance. And we're estimating the distance based on the scale to be 75 miles. And you see that this gradient, I don't want to call it gradient, I'll call it directional derivative, is 0.13 degrees Fahrenheit per mile. Now, usually when we are computing, not estimating the directional derivative, we have a formula and we have a function f. And so here's a theorem that we usually use to do the calculation. And here is a proof of the theorem. But let's just deal with the theorem right now. So if f is a differentiable function of f and y, then f has a directional derivative in the direction of any unit vector, and the unit vector here we're taking to be pointy bracket a and b, but I am emphasizing that this is a unit vector because this is just telling us the direction. So the directional derivative in the direction of u of f of x y is equal to the partial of f with respect to x times a plus the partial of f with respect to y times b. Now, you should note that this really is could be viewed as doing something, being taken dot product with the vector u, which is AB, and in fact we're going to do that later. So anyway, this is the formula that we use. Now, if the unit vector is making an angle of theta with a positive x-axis, and in fact we saw pictures of this earlier, then we can write, and we know that a unit vector then is going to be pointy bracket cosine theta sine theta into pointy bracket. And so what I can do then is I can substitute into this formula, and I have that the directional derivative u in that unit direction is given by f sub x, that is the partial of f with respect to x times the cosine of theta plus the partial of y, partial of f with respect to y times the sine of theta. And these are very much the computational formulas that you will be using. So here's a problem for you to undertake, and I encourage you to do it. Find the directional derivative, the derivative in the direction of u, of f of xy if this is our function, f of xy, x cubed minus 3xy plus 4y squared, and u is the unit vector given by the angle, where theta, and this was what we were talking about before, is pi over 6. And then, not just finding that directional derivative as a function of x and y and theta, perhaps actually theta will become a number because you'll substitute in the cosine and sine, but also find out what is this directional derivative evaluated at the point 1, 2. So that's taking x to be 1 and y to be 2. You know what to do. Let's see how you did. All right, so here's the formula we're doing. We know that the cosine of pi over 6 is root 3 over 2. The sine of pi over 6 is 1/2. The derivative of f with respect to x is going to be 3x squared. And then with respect to x, it's going to be minus 3y. And the derivative of f with respect to y is going to be minus 3x plus 8y. So then I simplify this, I factor out the 1/2, and I have this as my expression in x and y. But then what I can do is I can substitute the point 1, 2 in and do the calculation, and I find that the directional derivative in the direction of u, that unit vector that I was talking about, evaluated at 1, 2 is, and you plug it in, and this is the exact answer. And this is very typical of a kind of problem I would ask you on the tests or assessment doing the calculation. And you see that it is, again, formed by, here's our surface, there's the plane that is in the direction of that unit vector, there's a curve formed, and that's the tangent line at that point. So that's, again, re-emphasizing our geometrical interpretation of the problem. Now, before I talked about there seemed to be an emerging dot product, and in fact we codify this by defining what's known as the gradient vector. This is very important, so please pay special attention to this. Okay, so in that theorem we talked about the directional derivative of a differentiable function could be written as a dot product of two vectors. And here are the two vectors. One of them was u, which was pointy bracket AB, that was a unit vector. But the other one was the vector pointy bracket, the function, the partial derivative with respect to x, comma, the partial derivative with respect to y, but these were in pointy brackets. So it's the dot product of the two. Now, the first vector in this dot product occurs not only when we're computing directional derivatives, but in many contexts as well. It's a very important mathematical thing, so we'll give it a special name. It is called the gradient of f. Now, if you take the gradient of f, you get a vector, and there's a special notation, and sometimes it is written as GRAD for gradient, abbreviation of f, or sometimes it is written with this Greek symbol, which is an upside down, I don't know if that's isosceles or equilateral both, but anyway, an upside down triangle, which is the Greek symbol, and that Greek letter is called del, so sometimes that's written del f. So here is the definition a little bit more rigorously. If f is a function of two variables, x and y, then the gradient of f is the vector function del f. So notice you start with a regular function, but then you take the gradient and you have a vector function defined by the gradient, or del f of xy is pointy bracket fx at f sub x, the partial with respect to x, in the and then it's the partial with respect to y, and those are in pointy brackets, or written in IJ notation, we get this. So that's the definition of the gradient, so please keep that in mind. And so here is a problem. So if we said we had a function f of xy, and this is a function, it's z equals f of xy, is going to be sine x plus, and this is e to the xy, then the gradient is going to be pointy bracket. We take the partial with respect to x and the partial with respect to y. So this is going to be cosine x plus y e to the x. And then with respect to y, it's just going to be x e to the xy. And if I'm evaluating this at the point 0, 1, I put x to be 0 and y to be 1. We get this is the vector 2, 0. So with this notation, then, we can redefine the directional derivative, and this really is the computational formula you're going to be using most of the time, is the directional derivative in the direction of u of f of x, y, is the dot product of del, or the gradient, f of x, dotted with u. This expresses the gradient in the direction of a unit vector u as the scalar projection of the gradient vector onto u. And that's going back to previous kind of terminology that we've used. So here's a problem for you to try. Find the directional derivative of this function f of xy is x squared y cubed minus 4y at the point 2, comma, minus 1 in the direction of the vector v equal to I plus 5j. You know what to do. Let's see how you did. Now, one of the things you have to do is remember that the directional derivative is always in terms of the unit vector, so you have to turn 2i plus 5j into a unit vector. So we normalize this vector before we take the dot product. We also have to find the gradient. So what we're going to do is we're going to take the partial of this with respect with respect to x, and we get 2x y cubed, and then we take the partial of that with respect to y, and we get 3x squared y squared minus 4, and this is in the I direction and that is in the j direction. So this is what the gradient is when I substitute 2 and minus 1 in. And so this is going to be negative 4, pointy bracket, negative 4, 8. But then I'm going to take that pointy bracket, negative 4, 8, dotted with the unit vector here, finish the calculation, and we get my favorite number, 32 over the square root of 29. Now, this is the exact answer, and on a test or assessment, this is probably what I would expect you to do. Now we should note that the gradient could be, and in fact the gradient is a two-dimensional vector in this case, even though this was z equals f of xy was a three-dimensional curve. So it makes sense for us to think about that these vectors are two-dimensional vectors. So the two-dimensional representation of the surface is often shown in terms of the contour plot. And so here you show them superimposed on a contour plot, and both of these are in two directions, x and y. So I'm really emphasizing that the gradient is, in this case, a two-dimensional vector. Now, we can do the same thing, though, in higher dimensions, and we do. So, for example, we can define a directional derivative as this limit in a given direction, and this is in the direction of a unit vector that is pointy bracket a, b, c. Again, it's a unit vector, and I define the directional derivative conceptually exactly the same way. We're going not on the x and y necessarily, we're going in the direction of a, b, c. And so writing that as a vector equation, we could write it this way. And if we expand the definition of the gradient to be in three directions, so you see the gradient of f here is pointy bracket, partial with respect to x, partial with respect to y, and partial with respect to z. And notice that this is in four-dimensional space because x, y, and z are all independent vectors. So now what I'm going to do is I'm going to have this as my definition of the gradient in three dimensions, and you could even do this in higher dimensions. And then I'm going to dot product that with the unit vector to get the directional derivative. And here I'm saying that. So the directional derivative of u in the direction of u of f of four variables is this gradient dotted with this unit vector. Why don't you practice that on this example? Here you have f of xyz is x times sine of yz. You define the gradient and the directional derivative at a specific point in the direction of this vector. You know what to do. Let's see how you did. Okay, when we take the gradient of f, then we're going to have pointy bracket sine yz, xz, cosine yz, and xy, cosine yz, end of pointy bracket. And we're going to be evaluating that gradient when x is 1, y is 3, and z is 0. And so when we evaluate that, we get this as the vector. It's pointy bracket 0, 0, 3. And we have to turn this into a unit vector by normalizing it. And so we normalize it here. The length of it is root 6. So when we take those two things, you see the only non-zero thing is in the k direction here. That actually happens in some important applications we'll talk about later. And so you're going to have 3k dotted with that, and when you take k dotted with I and j, that's 0. So we're really just taking 3 times this. And you could have written this answer differently. It's minus 3 over root 6, but then if you do some fancy radical things, you could write it this way as well. This answer, 3 over root 6 minus 3 over root 6, is every bit as good as this answer as far as I'm concerned. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.